So this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we'll go through what you need to know for the upcoming test. So I'll divide this video into 3 sections. We'll do scientific notation, which also includes significant figures. Then we'll go through the index laws. It turns out there are 7 that you need to know. And finally, we will go through SERDES. So let's get started with scientific notation. So let's say I have a really large number like this, and I'm actually just making up digits as I go along. So it would be really hard for you to try and remember this number, say, tomorrow, because there's lots of digits, lots of different digits. But the idea here is that rather than trying to remember all of the digits, you might be better served just to remember the first few digits and how many digits there were, because how many digits there are tells you, is the number in the millions or the 10 billions or the 100,000s or whatever. So the idea behind scientific notation, a number like this, you could just remember it's about 7.8 billion, and that's close enough. So we use scientific notation for really large numbers or really small numbers like this. So there is a convention as to how we write the numbers that makes them easier to work with, easier to remember, easier to compare. So it's important we follow the convention so we can compare them easily. So the convention for scientific notation is you write the first few digits in the first box and you times that by 10 to the power of something. So what goes in the first box is a number between 1 and 10. So this number is usually a decimal. What goes in the second box up at the power is a whole number, and that whole number is positive or negative. So sometimes will be positive, sometimes will be negative, and I'll show you how to fill in those boxes in a second. So the idea here is we put the first few digits here, and then we put a number here that tells us how many digits there are, and that allows us to tell what the number is around about very easily. So let's look at the first example. So how would I put that in scientific notation? Well, you know that that can be written as the same number with a decimal point at the end. We can put the decimal point at the end of whole numbers. So what we need to do in order to get the number between 1 and 10 is we need to move the decimal point. So I keep moving it until the number's between 1 and 10. So if I move the decimal point 1 spot over, the number's still way too big, way bigger than 10. So I keep going. So even if I move the decimal point all the way here, the number would be 7,838 point blah, blah, blah. It's still way more than 10. So I have to keep moving it until it's here. If I move the decimal point here, the number I have is 7.838 blah, blah, blah. It is a number between 1 and 10. There's no other place where I could move the decimal point to make this number between 1 and 10. So when you have moved the decimal point to make the number between 1 and 10, that number goes in the box. So the number that goes in the first box is 7.838190423. So I'm writing all digits here. So what goes in the second power box is how many times you moved the decimal. So I moved it 1, 2, 3, 4, 5, 6, 7, 8, 9 spots. So I put a 9 there. So how do you tell whether or not the number that goes in that second box in the power is positive or negative? So if you moved the decimal point to the left, the number in the second box is positive. If you moved it to the right, the number in the power box is negative. In other words, if the number is greater than 1, when you started like a whole number, then that means the power is positive. the power being the number that goes here. And if the number is less than 1, then the power is negative. So using either of those definitions, I moved the decimal point to the left here. The original number was much greater than 1. It was a big number, so the power is positive, and I'm done. So that is in scientific notation, 7.838190423 times 10 to the power of 9. So what that actually tells us is that the number is 7.838 billion. Much easier to work with than just a string of numbers. So let's now look at the smaller number, the number that's less than 1. So you don't actually do this any differently than how I just did it. So if I want to write this in scientific notation, it is some number times 10 to the power of something. Any number in scientific notation is always some number times 10 to the power of something. So what goes in the first box? So you move the decimal point until the number is between 1 and 10. So if I move the decimal point here, the number's 6.2518, which is definitely between 1 and 10. So what goes in the second box is how many places you move the decimal point. So I moved it 1, 2, 3, 4 spots. So I put a 4 in there. Now I look at my rule up here. So I moved the decimal point to the right. So the power should be negative. Another way to look at it, the original number was clearly less than 1, so the power should be negative. So 0.00062518 in scientific notation is 6.2518 times 10 to the power of minus 4. Now what you might be thinking is, do I really have to write all of these digits and all of these digits? Well, no. What we usually do is we round it to a couple of significant figures. So the rule for you in this test, anything is significant except zeros to start a number. There is actually, no convention about zeros at the end of a number, but we're not going to get into that. So for your purposes, count any digit as significant as long as it's not 0 at the start of a number. So what I mean by that is, if we look at this first number here, all its digits are significant. This has 10 significant figures. When we put it in scientific notation, this has 10 significant figures. So when you're rounding to significant figures, you have to count the numbers before the decimal point as long as they're not 0. So that 7, even though it's before the decimal point, counts as significant. So that's different than when you say round to 3 decimal places. So this here has 10 significant figures. If I wanted to round it to, say, 3 significant figures, so I start off by writing 7.8, so that's 2 significant figures. Now to get the third significant figure, you need to look at this fourth significant figure. Just like when I'm rounding decimals, we use the rule 5 or more raise the score, 4 or less leave the mess. So this is obviously greater than 5. So the third significant figure I'm going to round up. It's not going to be 3, it's going to be 4. So to round this number to 3 significant figures would be 7.84 times 10 to the power of 9. And that's saying the number is about 7.84 billion, okay? So, to 3 significant figures, I just write that. So if we look at the second number here, it's got 5 significant figures. These 5 digits here. All the zeros at the start of a number do not count as significant. So similarly, when I write it in scientific notation, it has 1, 2, 3, 4, 5 significant figures. I count the thing before the decimal point. So if I wanted to round this to 3 significant figures, I would take the first significant figure and the second one and write them. So the fourth significant figure is this time less than 5. So 4 or less leave the mess, so I don't round the 5 up, I leave it as it is. So to three significant figures. This number here is 6.25 times 10 to the power of minus 4. So 10 to the power of minus 4 is a 10,000th. So this is basically saying the number is around 6.25 10,000ths, okay? So that's all for scientific notation. Let's get into the index laws. So in order to understand index laws, we need to know what an index is. So you probably know that if I have something like y to the power of 3, it means you times y by itself 3 times. It means you times this, which is called the base, by itself this many times. And this little number at the top is called the index or the power or the exponent. I'm just going to call it the index because we're talking index laws. So something to the power of something, if it's written like this, that is index form. And if it's written out like this with the multiplications, that's called expanded form. So make sure you read the questions carefully in the test. Is it saying give your answer in index form? A lot of the questions will say that. That means your answer needs to be written as something to the power of something. If it says evaluate, that just means give the answer or give the value of. So if I say evaluate 2 to the power of 3, you just write 8. All right, let's look at the index laws. So let's look at the first index law. So if we multiply bases together, we keep the same base and add the powers together. So an example of that, if you have like x to the power of 7 times x to the power of 3, keep the same base and add the powers together. How easy is that? So secondly, if you divide bases like this, remember a is the base because it's a thing being raised to a power, you keep the same base and subtract the powers. So if I had something like y to the power of 12 divided by y, keep the same base, subtract the powers. So y and y to the power of 1 are the same thing. 12 minus 1 is 11. All right, the third rule. So if you have a power, so I have a base raised to a power, and you raise it to another power, you keep the same base, but this time multiply the powers. So if I have x to the power of 7 to the power of 3, I keep the same base, but unlike in the first example where I added them, this time I multiply them. 3 times 7 is 21. So the fourth index law, anything to the power of 0 is 1, except 0 to the power of 0 is undefined. So 0 to the power of 0 is undefined. 2 to the power of 0 is 1. 4 to the power of 0 is 1. Minus 6.3 to the power of 0 is 1. Okay? 3 to the power of 0 is 1. You're probably getting the idea. Y to the power of 0 is 1, as long as y does not equal 0. So, fifth index law, if you have a product, something times something, and you're raising that to a power, raise the first thing in the product to that power, raise the second thing in the product to that power. So, for example, if I have something like 2x to the power of 3, people often mess this up. They think that it's 2x cubed, but the rule is you have to raise the first thing to that power, so that's 2 to the power of 3, and raise the second thing to that power. 2 to the power of 3 is just 8. Okay? So, second last index law. If you are raising a fraction to a power, you just raise the top to that power, raise the bottom to that power. So if you have something like, I don't know, x over y to the power of 4, just raise top to that power, bottom to that power, easy as. So the final index law involves negative indices. So if you have something to a negative power, you simply put it on the bottom of a fraction. So for example, 2 to the power of negative 1 is not negative 2, it's 1 over, so move the thing to the bottom of the fraction, write it with a positive power. X to the power of minus 5, move it to the bottom of a fraction, but write it with a positive power. So let's look at a few examples that involve more than one of these index laws. Sometimes you will have to combine index laws. So if I have something like this, I need to use the power of a power rule to get rid of the brackets here, and then I use the multiplication rule. So the brackets would be keep the same base, 3 times 2 is 6. So that turns into this. I haven't done anything with the other thing yet. Now, if I want to multiply bases, I keep the same base and add the powers. How easy is that? So let's say I have something like this. 4x cubed times 2x squared over 8x. Okay? So, I've got a whole heap of numbers. If you have a whole heap of numbers, treat them separately to the pronumerals. Now, 4, 2, and 8 are not being raised to the power. Because they're not being raised to a power, they're not bases, and I don't need any index laws. I treat them as normal. 4 times 2 is 8. X cubed times x squared, keep the same base, add the powers. Okay, and now to simplify this, 8 divided by 8 is 1. X to the power of 5 divide x is just x to the power of 4. How easy is that? So let's have something like this. 2x over y squared to the power of 4. I need to use a few index laws here. So it's a fraction, so I need to raise the top thing to that power, and I need to raise the bottom thing to that power. So to do the bottom, that's easy. It's a power to a power. Keep the same base, multiply the powers. To do the top, I need to use the product rule. So I raise the first thing to that power. 2 to the power of 4 is 16. And raise the second thing to that power. And this can't be simplified any further. So let's say I have something like this. So here I've got something involving some negative powers. So when you have an expression like this, everything with a positive power goes on top of the fraction. Everything with a negative power goes on the bottom. But you write it now with a positive power. Okay, that's how you deal with expressions like that. So let's look at just a few quick examples now involving zero powers. So we know that anything non-zero to the power of 0 is 1, so 7 to the power of 0 is 1. If I have something like 7k to the power of 0, here, because of order of operations, only the k is being raised to the power of 0. So that thing in the square equals 1, so the whole answer is 7 times 1, which is 7. If I have something like this, this is equal to 1, because now I am raising everything in the brackets to that power. So anything to the power of 0 is 1, but you've got to make sure you know exactly what is being raised to the power of 0. In this one, only k is being raised to the power of 0. In this case, both are being raised to the power of 0. Okay, let's go through the final thing we need to, and that is SERDES. So in order to understand SERDES, we need to know perfect squares. So not all whole numbers are perfect squares. So the perfect squares are 1 times 1, which is 1, 2 times 2 is 4, 3 times 3, and so on. These are the perfect squares we need to know. And you should know them by now, since you're in year 9. Okay? So the thing is, if we take the square root of a number that's not a perfect square. So notice 2 doesn't appear on this list. 2 is not a perfect square. So if we take the square root of a number that's not a perfect square, that is a SERD. It is an irrational number. So the square root of 2 is about 1.4142, blah, 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 goes on forever. It's just easier to write it as the square root of 2. So we need to know how to do operations with SERDES. So when you're multiplying SERDES, it's easy. If you take 2 square roots and multiply them together, it's just the square root of the 2 numbers together. So for example, square root of 11 times the square root of 2 is the square root of 11 times 2, which is 22. That's pretty simple. So it works for division 2. If I want to take square root of a divide square root of b, it's just the square root of the first number over the second. So for example, the square root of 120, so that again is a SERD because 120 is not a square number. If I divide that by the square root of 12, That's just the square root of 120 divided by 12, which is 10. So multiplication and division is easy. That allows us to simplify SERDES. We simplify SERDES, we want to not change the number, but write it so the number under the square root is smaller. Just like when you simplify fractions, you want the numbers in the fraction to be as small as possible. So just like with fractions, you can't always simplify a fraction, like 2 over 3 you can't simplify. You can't simplify all SERDES. You can only simplify a SERD if it has a factor that is a perfect square. So to check whether or not you can simplify a SERD, you need to find whether it has factors that are any of these numbers. We're not interested in 1 though, because that wouldn't actually change the SERD. So for example, I can simplify the square root of 90, but I can't simplify, the square root of 91, because 91 doesn't have any factors in this list. There are no square factors of 91 other than 1, but 90 is divisible by 9. So how do I simplify it? I use my multiplication rule here. Square root of 90, I write it as square root of 9. I chose 9 because it was a square factor that goes into 90. But square root of 9 is just 3. It's a whole number. So square root of 90 is the same as 3 times the square root of 10. They are the same things, but this one is said to be simpler because the number under the square root is easier to deal with. So if I want to go the other way, let's say I have something like 2 root 11 and I want to write it in a less simple way as the square root of a positive whole number, I just put the 2 under the square root, but I need to square it. The reason is I don't want to change the value of the number, and squaring and square root undo each other in exactly the same way that multiplication and division undo each other, or addition and subtraction undo each other. So to move the 2 under the square root, I need to square it. Square root of 2 squared is 2. And then I still have the 11. So square root of 4 times 11 is just square root of 44. So if I wanted to simplify square root of 44, it would be 2 root 11. Okay? So that's how you multiply and divide and simplify. Let's now look at addition and subtraction. Unfortunately, addition and subtraction is a little harder. So just as you can only add or subtract like terms in algebra, you can only add or subtract like SERDES. So what makes SERDES like SERDES? The same number under the square root. So I can add, say, square root of 2 and 4 times the square root of 2. Okay? Because they are like SERDES, they both have a 2 underneath the square root. So just like when we're adding or subtracting terms, we just add or subtract the numbers in front of the SERDES. So square root of 2 is the same as 1 times the square root of 2. Sorry, that should say in front. So that just simplifies to 5 root 2. If I have like 3 root 7 minus 2 root 7, 3 minus 2 is 1. Root 7. If I have something like root 2 plus root 3, I can't simplify that because this has a 2 underneath the square root, this has a 3, they are not like SERDES. Can't simplify it any further. I can't write square root of 2 plus square root of 3 as the square root of just some positive number. So what makes this especially complicated? Yes, you can only add or subtract like SERDES, but sometimes you can simplify a SERD so that they become like SERDES. So let's say I wanted to simplify something like square root of 125 minus, let's say, 3 root 20. Now, it probably looks like these are not like SERDES, because one has a 125 underneath, the square root, one has a 20. In the previous example, I said you couldn't add or subtract surds if they're not like surds. But the thing is, if I simplify this surd and this surd, they will become like surds. So the difference is, in the previous example, I couldn't simplify root 2, couldn't simplify root 3. That's why I couldn't add them together. But here, I need to first check whether I can simplify, and I can. So to simplify square root of 125, you need to find the highest square number that goes into it. So 1, yeah, we don't care about. 4 doesn't go into it. 9, 16 don't go into 125, but 25 does. So I'm going to write this as square root of 25, because that's a square number, times by, so what do I need to times by 25 to get 125? The answer is 5. So this is 3 times now root 20. What is a square number that goes into 20? Well, that's 4. So I write it as square root of 4 times, so what do I need to times by 4 to get 20? Of course, 5. But of course, square root of 25 is just 5. So that will become 5 root 5. Square root of 4 is just 2. So I have 3 times 2, which is 6 root 5. So as you can see, this and this can actually be subtracted because they are like surds after I simplify them. So 5 root 5 minus 6 root 5 is just minus 1 root 5, because 5 minus 6 is negative 1. Okay, I know surds are pretty hard. I know that index laws can seem hard too, and scientific notation, there's just a lot to remember. So please study hard and ask any questions. You're a superstar. You're going to ace the test. This has been the luckiest maths teacher in the world. Have a great day.